In this example, we want to find the linear approximation of f of x equals 12 minus x squared at a equals 2. Once we do that, we want to approximate f of 2.1 and then compute the percent error. Okay, so a lot going on here. Let's try to consider this visually and think about what's actually happening here. The function 12 minus x squared is a parabola that opens down. And of course, you could do all of this without visualizing the function at all. Just sometimes it's helpful to have a visual representation of what's happening. There we go. This makes a nice parabola here. Something like that. And what we are doing, this is about 2 over here. So we're finding the linear approximation right at this point. Something like that. So recall our equation for the linear approximation. The linear approximation of x at a is given by L of x equals f of a plus f prime of a times the quantity x minus a. Okay, so we just need to find all these values. We already know what a is. It's 2. That's given in the problem. And from that we can quickly compute f of a by simply plugging in 2 to this function. So that's 12 minus 4, which is 8. Okay, so there's our f of a. F prime of a is found by taking the derivative of the function. So f prime of x first is negative 2x. So then f prime of a, well, that's f prime of 2, which is negative 4. Now we're ready for our linear approximation here. So let's see here. L of x is f of a, well, we decided that was 8, plus f prime of a, so that's negative 4, so I'll make that minus 4, times the quantity x minus 2 because a was 2. Alright, let's clean this up and get it into y equals mx plus b form, just because that's more of a recognizable way of presenting lines. So let's see. We have 8 minus 4x plus 8, so that gives us negative 4x plus 16. There is our linear approximation. Let's look at this on Desmos to see what these two look like when they're graphed together. Okay, here we are, and you can see right at the point x equals 2, I guess the point is 2 comma 8, the approximation right around here is really nice. You can't even tell the two functions apart if you're close enough to this point 2 comma 8. The further you get off, the worse the approximation gets. Right over here, imagine how bad it would be at negative 10. I don't even want to think about how far off these two approximations are. So right around 2 comma 8 is a great approximation. On to the next step. Let's use our approximation to approximate f of 2.1. So what this is asking for is the linear approximation L of 2.1 equals what? Well, this business here, this negative 4x plus 16, that's our L of x. So now we simply plug in 2.1 for x. Okay, so that's negative 4 times 2.1 plus 16, which comes to 7.6 if you put that into a calculator. Okay, so there is our approximation. Let's see how far off we are. We use something called the percent error to do that. Here's an equation for percent error. Percent error equals 100 times the absolute value of approximation minus exact, all over the absolute value of the exact. Well, we already know what our approximation is here because we computed that. That's our L of 2.1. So that comes to 7.6. Our exact answer, we plug into the function. Remember f of x was, 12 minus x squared. So the exact is f of 2.1. Okay, and then we put that into a calculator. It comes to 7.59. Now, one could argue that if we already knew the exact, why would we work with the approximation anyway? And that is a good question. Moving on, we have 7.59 right here, and we'll put in 7.59 down here. Okay, so now we can compute our percent error to be 100 times the absolute value of 7.6 minus 7.59 all over 7.59. So those values are very close, right? 7.6 versus 7.59. So we know we're looking at a good approximation. When we run this through a calculator, you get about 0.13%. So that's the percent error, a very small percent. So that tells us this is a very good approximation, around 2.1, which makes sense because that's very close to 2. You can imagine that as we go further and further off from 2, this approximation would get worse and worse.